we discussed the RAM method of ADC, and you can understand why it is called the RAM method, because uh, you can see that uh, you go on increasing the count starting from 0, then you put a 1, then a 2, then you increment that by 1, 2. So what actually happens with time is that you begin building a ramp. So till you reach the appropriate, so first you are going step by step, you are adding 1, then you are adding another 1 to it, okay, then you're adding another 1 to it. So in this case we had 5, so 1, 2, 3, 4 and 5. So what you're achieving actually is, it's a ramp. This is what we call as a ramp, okay. So that's why it's called as the ramp method. And you're essentially just increasing your count, you are incrementing your count by 1. You can also look at it from a, like mechanical engineers, we would like to have very simple examples. So possibly you can also look at it like this, that we consider a certain, let's look at it as a balance, as a weighing balance. So we have say a weighing balance, and on this weighing balance, let's say we have a platform here, and platform here. And we have a fulcrum. So approximately, well, we can say that inside this fulcrum, keep it somewhere in the middle, and so we have this fulcrum, and let us say that we are going to place weights. So in our case, we had say 5 kgs here. Okay, we'll go in increments of 1 kg. So here we had 5 kgs. We could straight away take a block of 5 kgs. I will adjust the height later on, but let's say that for now, just to get an idea, this is corresponding to 5 kgs. Okay, and what the ramp method does is it takes weights, unit weights. It takes weights of just 1 kg, one at a time. So you're just taking a block of 1 kg first. Okay, then you are placing it over here in this pan, and then you are checking whether the balance is tilted or not, whether, so you are getting it in terms of count. You place this 5 kg, you did not know that it was 5 kg, you placed a weight. We know that it is 5 kg, but when you placed it, you did not know its weight. So now you are just adding a block of 1 kg. So this is 1 kg. Then you are checking whether the balance is tripping or not. Then, well, it's not. So you add, I'm sorry. So you add another weight here. You add another one according to this algorithm. Then you check again whether this works or not. No, it doesn't. It doesn't weigh. It doesn't trip. Then you again place another one. You check whether it has tilted or not. No, it has not. Place another one. Okay, so 4 are done. Again, you check whether it is okay or not, whether the weight has been achieved or not. No, it has not yet been done. So you place one more here. Okay, now it is done. So now you find that beyond this, if you add anything more over here, it is going to trip, right? So now this balance is okay. So maybe we can adjust the height of this and make this the same height over here, so that is what I told you in the beginning, that we just. So this 5 kgs is being written in terms of these blocks of 1 kg each. And we just count these blocks 1, 2, 3, 4, 5, and we know that this corresponds now to 5 kgs. And so then we say that, okay, this can be represented as digits, 5 decimal that corresponds to. So this is increments of 1 kg each. So here you go on adding these 1 kg weights, and you have a total of 5 kgs. And so you say that you are able to represent this as in 4 bits, you are able to represent it as 0, 1, 0, 1, because this is the digital representation of 5. This is the binary representation of 5. 5 in the decimal system. Okay. So this is what our ramp method is doing. Naturally, if our weight over here was 7 kgs, we would have to do this step 7 times. We would have had to place one, next, 7 times. So depending upon the magnitude that we have here, if we had a larger weight over here, we would have had to have so many more steps. And so that is what we discussed in our previous lecture, that the variable number of steps are required for the analog to digital conversion. And it could actually take a lot of time for higher magnitudes of the signal. So suppose if you had, instead of 15, say you have 13. So it will take 13 steps to reach 13. Whereas if it was just 3, it will just take 3 steps. So you are having a variable number of steps when you do the ramp method of analog to digital conversion. And naturally, it's going to take a lot of time if the magnitudes are higher. So this particular method is not commonly used. So this is actually an equivalent. This is just an example, a mechanical way of understanding the equivalence of the ramp method. Okay. Now, this is one way of looking at it. Now, suppose we uh, see, we are interested in digitizing this in terms of bits. Now, here we did a 4-bit representation, and therefore we got this bit pattern. Suppose we uh, have a we come out with a way which is going to take the same number of steps for any weight. Okay, will that not be more convenient? It certainly will be more convenient. So there is such a method, and that method is actually called a successive approximation method. It's a method of successive approximation for analog to digital conversion. Now, in that method, what we do actually is something like this. Um, we will, let's say we have this 5 kgs here, but we want to understand this representation. So we know that we have 4 bits, and in this digital representation, we will provide weights. So let us say that for uh, take so we will prepare these weights like this. So we have a 1 kg weight already available with us. Now we will take a 2 kg weight. So we are going to reduce this slightly, a little more. Okay. So now it is 2 kgs. Then we will have one more weight like this. So we will keep a 2 kg weight over here. We will also have a 1 kg weight. We will break our weight into a number of smaller denominations. But these denominations, they are going to be these standard denominations. We either have 1, or we have double of that, or we have further another uh, double of that. So this is 4. We'll place this here. I'll just shift the location of this a little. And we'll double this one also. Let us say so we have 8 here. Now it's, how are we going to start the measurements? You can write down these denominations, these weights over here. This is 1 kg. This is 2 kgs. This is 4 kgs. This is 8 kgs. You can have weights in this manner only. Now, in the method of, so this was the ramp method. Now we will try to follow the method of successive approximation. So I'm first going to just explain to you what is it. So we are just finding out the equivalence of the successive equivalence of the method of successive approximation. Successive approximation. So we take the same balance as we had before. And we will keep it here. And then we will take our weights which we have prepared here. Let's keep them ready here. Shift this title. So, so now we have this weight of 5 kgs and we are going to place it here. And we want to know in terms of these standard weights. These are the standard weights which are provided to us, one each only. Okay. So how are we going to proceed? First of all, we will take the most heaviest weight corresponding. It's a 4-bit representation. So we'll take the heaviest weight for 4 bits. So we have 4 options before us: 8, 4, 2, or 1. We will take 8. We will place 8 over here. Okay. The moment you place 8 over here, you can see that this 5 kgs, here we had 5 kgs. Sorry. So this was 5 kgs. And here we have 8 kgs. So naturally it is not going to, it's going to trip. So this is not acceptable to us. So we cannot take this. We cannot consider this weight. Okay. So we will take this out from our representation and replace this. We will just keep them handy here. We could keep it here itself. I'm making this platform slightly bigger. Okay, so we place it here. Out of this, I'm taking off this 8 kgs because this is not serving our purpose. So this 8 kgs is gone. Okay. Then right now, then we'll try out the 4 kg weight. Now, when we try out the 4 kg weight, so that is the next bit. Now you see that the balance is not tripping. So this is 5 kgs, this 4 kgs. Actually, this is heavier. It doesn't tilt. So we will add the next bit, that is 2 kgs. So we'll place the next bit over here, that is this weight. Sorry. So now we will take the 2 kg weight. This 2 kg weight. Place it here. Write it by hand. So this is 2 kgs. So now on the right hand side you have got 6 kgs. Here you have 5 kgs. Naturally the balance is going to trip. That means you can't use this 2 kgs. So we will have to leave this particular slot blank, just like we left the previous slot blank. Okay, here we had to leave it blank. Blank we will represent, say, using a straight line preferably. So take a straight line of the same length and this blank is kept here. The same way we have another blank. But now it has to replace this 2 kgs. It will come over here. So there's another blank. And then we will place the next, that is the 1 kg weight here. So we'll take the 1 kg weight and we'll place it on the pan here in this position. Okay. So here now we have 1 kg. So this is 1 kg. Now you see on both sides you are having 5 here and you are having 4 here. 4 plus 1, 5 here. So now it is balanced, and so we can say that we have got 5 kgs. So this weight which we placed over here, which we did not know the weight of, in terms of these standard weights, it is 4 kg plus 1 kg, that is 5 kgs. Okay, so 4 kgs occupies this position. So wherever in this 4-bit representation, we can say that this 8 is not here. Okay, so this is wherever we have a weight, we will place 1 over here. So we have no weight here. We have a 1. That means there is a weight here. There is no weight here and there is a weight here. Okay. So these are the standard weights. And naturally, this is telling us that this is the digital representation of 5. It's in terms of this. So this is what actually the method of successive approximation is. And how are we going to implement it in actual, in a schematic? Let's see that. So we have some time. Let's just discuss this aspect as well. Let's modify this figure itself, perhaps. Yeah, let's take a copy of this. We just modify it a bit. So erase this. This is method of successive approximation. And quite a few things we can take from our previous slide itself. We'll just make modifications to this. So we'll keep the same logic as far as the comparison is concerned. So here, let's say this is our analog input signal. Which has to be digitized. And take the signal, and after sampling it, we'll hold the signal till the process of the conversion is complete. Here we are going to use a comparator. So this is our comparator. And the comparator is going to give us either a 1 or a 0, depending upon whether Vs is greater than dA or Vs is less than or equal to dA. So we will pass this on to so we could make use of this. So we have a 4-bit register here, and this register we'll call as a successive approximation register. It's because we want to digitize the signal in 4 bits. If we were required to digitize in 8 bits, then we'll have an 8-bit register here. Okay? And we'll also have a 8-bit digital to analog converter. But now, because our example is for 4 bits, we're going to have this as a successive, abbreviation is like this, successive approximation register, SAR. And we take the analog signal, let us say this analog signal, we need to tell this circuit when to start. We have to tell the sample and hold when to start, and we have to tell this successive approximation register when the process is going to start. So for that, we need a start conversion signal. Okay. So we'll have to start the conversion. So you need a signal for starting the conversion. Start conversion. It's just like you're pressing a button and a high is generated. So start conversion signal. But this signal has to be sent so that at that instant you're going to obtain the sample. So this signal we're going to take it from here and we will pass it on to a unit which we will call as a control unit, because that has to control the process, it has to control the algorithm. Okay. So this is our signal, start conversion signal. And so we will send this to the control unit. And we will also pass this on to the sample and hold, because the sample and hold also should get an information when to do the sampling. So we'll take the same signal and we'll also pass it on to sample and hold circuit, and we'll let it know when to do the sampling and to hold it. So this is our sample and hold. So it gets the signal over here. Now, this control unit also will put it in a box just to represent. And from this, this control unit is also going to pass on an information to the successive approximation register. So it is going to tell okay, and it's also going to, once the process is over, we should get a signal from the control unit that the process is over. So we will also have an end of conversion, a signal indicating that the conversion has ended. So it will do it in 4 steps because we have 4 bits, and it will indicate to us. So we will have an end of conversion here. We need a signal for that. So end of conversion. And When the conversion ends, okay, this the contents of the successive approximation register have to be latched. So that indication has to go from it has to go from the control unit. So we'll pass on from the control unit uh, the latch. Pass an information on to a latch. We have the latch here. This will just latch these digits. So we take the signal. And latch it at the end of conversion. So okay. And here we will take the output. The latching is over. Take this out. So this is our digitized value. It is the digital output that this latch will provide to us. So this is our digital value. Okay. And let us designate. We'll of course have to remove this older stuff which is here. Now we'll erase these statements also. We'll write them afresh, whatever observations we have as far as. So these we can write afresh. And of course, the algorithm also will change. Uh, Now we don't have these constraints with us. So we will change this one. And we'll also not need to increment because we are not doing counting. We're not going to implement this over here. And of course, yeah. So let us write down the steps. What happens? We start with the most significant bit. Okay. Let's designate the bits also. Let's say this is corresponding to B0, this is B1, this is B2, and B3. And this is, let's say, A0, A1, A2, and A3. So in our example, what are we going to do? We'll first, now we'll start with the most significant bit. That means we will set I equal to 3. We'll set an index I as equal to 3. Okay. And then we will, this corresponds to our MSB. So we'll set the MSB to 1. That means AI, which is actually A3, which is also our MSB. We are starting with the most significant bit. I'm writing it as most significant bit. Okay. Most significant bit, we will set this as equal to 1. And then we will send the output. We will send output through DAC. Okay. So when you send the output, you will have 1 0 0 0. Okay, to start with, that is 8, and 8 is now being compared. So the digital value that will be sent, the analog value corresponding to 8 will be sent out. So here on a scale of 0 to 15, you are comparing 8 with 5. So naturally, this is going to be 0, and you are not going to pass through this step. Rather, you are going to pass through this. And so in this particular case, you will have A3 as equal to, so if VS is VDA is greater than this, so you are getting a 0. Yeah. So on this account, you are going to get A3 is going to be retained as, so you're going to retain this A3 will be, sorry, A3 will be made 0 because it is corresponding to 8. You will then try out the next one. So you will do this, you will repeat the process for the next bit. First, and here you will make A2 as equal to 1. And then you will obtain what should be the n, what should be the number that is so generated. So here now you have 0 1 0 0. So when you have sent this out through the, so the arrangement will be A3, which is equal to 0, A2, which is equal to 1, A1, which is equal to 0, and A0, which is also equal to 0. So here you are having now 0 1 0 0. So you send this out. Okay, and so we have to output this n. So we will output this n through our DAC. So now it will give 4. It will compare with 5. So it will give a 1. And when it gives a 1, here this, just like we did earlier, you will then try the next. So here you will get 0 1. Then you try the next bit. So try the next bit corresponding to I equal to 2. So here this bit corresponding to I equal to 3 is retained because here you have got this, and then you take I equal to 2. So this will be A1, I equal to 1. So here you will take this as 0. So 0, 1, 1, 0. So again, this is greater than this. So again, it will produce a 0. It will produce a 0. So here you will have 0, 1, 0, 0. Then again you will place a 1. Okay. So you are going in steps. What you are doing is first you are placing a 1 here. So this corresponds to 8. Okay, you are sending the output. 8 is heavier, so this does not work. So you are replacing it with 0. Then you are setting the next bit as equal to 1. This corresponds to 0, 1, 0, 0. So you are having 4. You are making the comparison. You can accept this because it is less than 5. Then you put the next one over here. So it generates 0, 1, 1, 0. It is sent out through the DAC. Here you get 6 because 0, 1, 1, 0 corresponds to 6. But 6 is heavier than 5. And so this will be set to 0. So this will go set to 0. And then you put the last digit here. So here, when you set this 1, it will become equal to. So it will be equal to this. So it will go to this step. And so 1 will be retained. Okay. So you have 0, 1, 0, 1. And that corresponds to your digitized value of this analog signal for this representation, 4-bit representation in this range. So this is how the digitization is done. And you can see that you require just 4 steps, starting from the MSB, and you proceeded towards the LSB. So you got it in 4 steps, 1 for each bit. Okay. So that is precisely what we were discussing in our example of the weights. That's what we did. We first placed an 8 kg. It didn't work. So we put the next one, that is 4 kg. It worked. We needed to add more. So we added 6. We added 2 more. So it did not work. Then we had to add 1. So we proceeded in terms of these standard weights. Okay. So this method that we have just discussed, it's called the method of successive approximation for analog to digital conversion. And finally, the count that you get here, is the digitized value of your signal. What are the aspects of this method? What are the points, highlights of this method? One is that in comparison to the previous method, it takes the same number of steps. Okay. Takes the same number of steps. It takes the same number of steps for any magnitude of the signal. Okay. The second aspect is that it doesn't, 4 steps is not much. if you are using a 4-bit register, if you are doing digitizing in 4, if you are using 8-bit register, then you will require 8 steps. If you have an n-bit register, n-bit representation, analog to digital representation, you are going to require n steps. So the number of steps is not much. Okay, so it takes comparatively lesser time. Analog to digital conversion. Okay. So these are two aspects. You can program this method and you can produce this. You can, when you do the microcontroller, you can use this, but of course, uh, there are channels for analog to digital conversion, and chips are available in which this logic is hardwired. So it is very easy for you to get this in hardware. These are low cost analog to digital conversion chips, and uh, the principle is what we have discussed over here. So this was our digital to analog converter. How to label this part. I hope the method is clear to all of you. Any questions? Yes? All of you, any questions so far?
So what is latch?
What is?
Latch, sir, latch.
Yeah, you see over here in our discussion, we need to retain this bit pattern. Okay, once the conversion is done, we have to retain this bit pattern. Okay, physically we say we have to latch it. So there is a circuit, a digital circuit available for latching. Okay, so you retain the contents of this, they get latched. Okay, so that they are available as in terms of the bit status. So 0 1 0 1, that's what the computer can acquire and understand. Okay, so this circuit is called a latch circuit. Okay, is it clear?
Okay, sir. Thank you. Yes, sir.
Any other query that you have? If not, then we'll conclude our class for today. I think we have exceeded our time. No more questions, then I will stop the recording and we will